In the previous lecture, we defined what it means to be a differential form on a Euclidean open set. So what we had was, we defined what is known as the differential form algebra of U, where U is an open subset of some Euclidean space. And what we are going to do today is we're going to define the differential form algebra of, let's say, X, where X is a smooth manifold. So technically, it should be X, comma, an atlas, a smooth atlas, but we usually suppress the smooth atlas. So that's what we're going to define. The idea is that a smooth manifold, it is made out of charts. So let's say you have like a torus, that's a smooth manifold, and then you're mapping Rn into the torus. So you have some kind of chart over here. And if you want to define a differential form on the entire torus, you just have to bring everything back to the Euclidean plane, or in general Euclidean space, and define everything on these Euclidean spaces. That's sort of the idea for why we talk about this first. But before we do that, I should have said something last time that I completely forgot. But before we do that, there is a simple comment that I want to start with that I should have mentioned last time, but I completely forgot to say it. And it basically has to do with this. So let's just go back to this again. Let's say that U is an open set in Euclidean space. Then the differential form algebra, this is the algebra generated. So this is the algebra over smooth functions that is generated by the symbols dx1, dx2, dxn. You can also use different letters, so you can call it dy1, dy2, dyn. It does not really matter what letters you use, but the number of generators that you need has to match the dimension of the Euclidean space. And satisfying the rule, satisfying some rules, which we're not going to write down again. Now, you might say, why not, if these are just symbols, why not just call these symbols like we do in a polynomial algebra? Why not just call them like x1 to xn? Or why not call them like d1, d2 up to dn? Why specifically do people always write it like this? And there is actually a reason for this. It has to do with the following, that let xi denote the projection map onto the ith coordinate. So in other words, this is the projection map that's defined on U. So if you give me a point in U, so pi1 of that point would just give me the ith coordinate that you see. So that's the projection map. But often, as is the case, we get sloppy in mathematics, and the formula for the function that we're using is the function. So if you have a coordinates of a point, then the function, it's the one that just extracts the ith coordinate that you see. So this is the projection function. Now, look what happens when you calculate the exterior derivative of this projection function. So this is going to give you a 1 form. So how do we calculate the exterior derivative? Well, that is by definition, we have to differentiate this function with respect to the first variable. Then we write down our differential, and so on. xn, dxn. And because this is the ith projection function, all of these partials are 0, except when you're using the ith differential, when you're taking the ith partial. So this is just going to be 1 dxi. All of the other ones are going to be equal to 0. So we see that when you take the ith projection function, its exterior derivative is equal to dx1. So to put it very simply, in other words, we're saying that dxi is equal to dxi. So it's two different meanings. This is the exterior derivative of the ith projection map that we just happen to denote by xi. And this is the ith differential symbol. So this one has, so it's basically, this is really, if you want to be a little bit more careful, this is d applied to xi, whereas this has to be taken as a whole thing together. That's just your symbolic. But you can see the notation works out correctly that dxi is dxi. So there's like two different meanings, but they coincide together, and there is no conflict in notation. So because of that, that's the reason why we denote the symbols that generate the algebra by using these symbolics. So that's the reason why we do it like that. So now let's get to defining what is a differential form on a manifold. Now, before we define what a differential form is, it would be helpful, to first define smooth functions on a manifold, where X is a smooth manifold. Maybe we should recall what a smooth manifold is. So it's really X, comma, an atlas, and an atlas is a collection of maps. Let's call them phi lambda. You could have an infinite number of such maps. So it's a topological space together with a collection of maps where each phi lambda maps Rn. So we're assuming that this is an n-dimensional manifold. By the way, this n will be fixed. So unlike in a triangulation where the dimension of the simplex depends on lambda, in an atlas they're all the same dimension. So you're mapping Rn into X, where each is a homeomorphism of Rn onto an open subset. It's an open subset of X. Maybe I should, that's redundant, under an open subset of X, so that X is then the union of all of these open subsets. So just like we have in a triangulation. And we have this condition that if you do phi lambda and you compose it with phi, let's say, mu inverse, this is a smooth map in the Euclidean sense. Okay. I meant to say smooth manifold. Manifold. So let's just go over that part again, what we mean by this. What we mean by this is that we have some kind of manifold over here, and we're mapping Rn. This is phi lambda, homeomorphically onto an open subset. This is X subscript lambda. And then we have another chart, so we call these charts, that maps Rn homeomorphically onto another open subset. Let's call that phi mu. We're going to assume that these charts happen. This is X mu. As you can see, I did not draw it properly. It escapes outside my space, but I'm sure you can imagine what I mean by that. So they happen to overlap. So the place where they overlap, so let's say this is where they overlap. So that would be X lambda intersect X mu. If you pull that back using phi lambda, because this is a homeomorphism, it will take you to an open subset over here. And if you pull that back using this chart, that's a homeomorphism, so that will take you to an open subset over here. And so you have a map from one open set to another open set, and that map is, so you're doing phi lambda first, and then you're going backwards by phi mu. So this would be phi lambda composed with phi mu inverse. So we need to understand that this composition, it's not actually defined on all of Rn, but it is defined in an open subset of Rn, and it maps that open subset homeomorphically to another open subset of Rn. Right, so it's just a homeomorphism between two open subsets of Rn. It could be defined in all of Rn, but usually that will not be the case. And the condition is that this is a smooth map. So this would just mean that it's smooth in the Euclidean sense. The partial derivatives all exist as many times as you want, and also the component functions are going to be smooth. So you're mapping. So to be smooth from Rn to Rn means the component functions have to be smooth. And the component functions being smooth just means the partials can be differentiated as many times as you wish. So that's the definition of a smooth manifold. Of course, if this intersection is empty, then there's nothing to check. So there's some books that will put the condition that assuming this is not empty, but I just like to write it like that because if it is empty, then it's just automatically true. Also, as I remarked, the way we're setting up our definitions, we're mapping Euclidean space into X, whereas there are some people who map the manifold into the Euclidean space by just using the inverse. It's just a choice of how you choose to set up these definitions. It's not that serious. Okay, so that's the definition of a smooth manifold. So now, let's define what it means to be a smooth map. So suppose we have a smooth manifold is a smooth manifold. How do we define a smooth real valued function? So the big idea is, and this is basically how everything comes back to manifolds. So the big idea is, when dealing with manifolds, and when I say manifolds, I mean smooth manifolds, but from this point on, I will just call them manifolds. When dealing with manifolds, you convert every problem back to charts, and then interpret the question in the Euclidean way. So what do we mean by that? Well, we have X, and it's being mapped to R, and this is F, and the question is, what does it mean for this to be smooth? This is an abstract space. How do I calculate partial derivatives of X? That makes no sense. But what does make sense is you map Rn into X by using the lambda chart. So phi lambda, that's the lambda chart. So that will map it into X. And if this is to be smooth, then it makes sense the composition should be smooth. And then you're getting phi lambda composed with F. And you're getting that this is smooth. So the definition is just this composition. So you see, you're bringing it back to the Euclidean space. And then you know how to answer the question of smoothness in the Euclidean space. So I should have said, how do we define from X to R to be smooth? And we are being a little bit sloppy, but really it's X comma the atlas. If you use a different atlas, then you might get a different answer. It's all dependent on the atlas that you pick. So the way you do it is you just do it like this. You just say that, so F from X to R is smooth if and only if F composed phi lambda, and this is a map from Rn to R, is smooth for all lambda. So that's how you define smooth. But I'm going to give you an alternative definition. Okay, so let's call this definition 1 for being smooth. And now I'm going to give you an alternative definition. And the alternative definition, you can argue, is more convenient, because that's the way we're going to do it for differential forms. So let's just write down the definition and think about it. So let's just remove all of this and we'll begin again. So this is just the first definition. You say a function from X to R is smooth if and only if its composition with every chart is smooth. And here smooth means smooth in the classical Euclidean sense. So here's the alternative way to do it. So let x comma phi lambda be a smooth manifold. So to define a function from x to r, it is sufficient to define a function in each chart. So i.e., we want to define a function from Rn into R for each lambda. So let's call this function f subscript lambda, because we're doing it for every chart. So what's the idea? So let me draw a picture for you. Here is our manifold, and I want to define a function going into R. So instead of defining a function from the manifold into R, I can do it differently. I can go into my chart, and I can define a function from the chart into R, bypassing the manifold. Now, what's the idea? Well, the idea is because this is a chart, it is being mapped into your manifold. And so if I want to be able to say how to map a point, so if I want to be able to define a function from x to r, basically what I do is I pick a point in x, I pull back that point through the chart, and then I use f lambda, and I've defined the function from x to r. Now the problem is on the overlaps. So let's go back to the torus again. I want to define a function from the torus into R. So how do I do it? So I'm going to pick a point on a torus. How do I map? Where do I map that point into R? Well, what I can do is I can pick a chart. So this will be R2, and I have phi lambda. But I can also pick a different chart, and maybe I have phi mu. And then that point, it belongs to two different charts. So if I know how to map a chart, so let's say I have a map into R, f lambda, and I have a map from this chart into R f mu, then the idea is that if I want to map this point on the torus to R, I can pull the point back to the lambda chart and then use the lambda mapping to map it into R. Or I can pull the point to the blue chart and then use the other mapping to map it into R. Well, we want this to be consistent, because otherwise we're going to have a problem. That we want to make sure that if the images of the charts overlap, then these two functions, the way the function is being defined on the lambda chart and on the mu chart, we want these functions to be consistent with one another. So to define a function from x to r, it is sufficient to define a function in each chart. So for every chart, we have a function f lambda. But we want this collection of functions to be consistent. You can also say coherent. So what do we mean? So in other words, here's what it means. So we have, so what we have here is we have, so the place where they intersect, so this is the place where they intersect. So here's the open sets where they intersect. We have a map here, which we call phi lambda composed phi mu inverse. So that's the mapping from this open set to that open set. And we want, so maybe if I can get rid of all of these extra arrows because they're just getting in the way, we basically want this diagram to commute. So the mapping that, so the answer that we get by using that mapping and the answer that we get using this mapping should be consistent with one another. So the condition should therefore be what? It should be that, so we want that if you do that f lambda should be equal to f mu composed with this. So if this condition is satisfied, then we have a well-defined function. Okay? So this is what we have. So if this condition, so this is coherence. This is what we call coherence. So this is what we call, this is the coherence condition. If this condition is satisfied, then we can define a function, a real valued function from x to r in a well-defined manner. So what do you do? Well, basically all you do is, if you give me a point P, how do I map P into R? Well, the point P is in some chart. So there's some chart Rn. There's this lambda chart that contains the point P. Let's call this X. So X gets mapped to P. And then I know how to map Rn into R because I already have a function that does that for me. Right? I have a collection of functions in each chart. So I bring the point back into the chart, and then I use the f lambda to send it forward. And it does not matter what chart I pick, because if I use a different chart, this condition is satisfied. And so I end up in the same point again. So this is an alternative way of defining a smooth function. So here's an alternative way how to do it. So this is definition 2. So let's say definition 2. You can say a smooth map or smooth function from x to r. And again, it's x with an atlas is a collection of smooth functions. Let's call it f lambda, where each f lambda is a smooth function in the chart, right? So basically, what we're saying is you pick a family of smooth functions in each chart. That's the idea. So that's the big idea about manifolds, that you always bring things back into the charts. So instead of defining what it means to be a smooth map from x to r, you rather define a collection of functions in every chart, because these charts are then being mapped into x. So it's a collection of smooth functions, and this collection is coherent with respect to the atlas. So our atlas here is this. What does it mean coherent? It means, i.e., if you have f lambda and you have f mu, what's the condition that has to be satisfied? So the condition here would be that if you have f mu inverse composed with phi lambda, then, yeah, so this is what we mean by coherence. Right? And if you forget how it goes, you just have to think of this. You map Rn into x, you map Rn into x, this is phi lambda, this is phi mu. So you have a map here, which is phi lambda composed with phi mu inverse. So you can forget about, you can forget about that. And if you have a map f lambda into r, and you have another map f mu into r, well, to be coherent just means the diagram has to commute. So f lambda should be this composed with that. So this composition has to be satisfied. Okay, so that's an alternative way of defining a smooth map. Okay, so this is going to be very helpful for us when we define what is a differential form on a manifold. So we have these two definitions, but this is the one that we're going to primarily be using. But before we move on and define what a differential form is, I want to give you an example. In this example, we're going to work with the circle again. The unit circle is a smooth manifold, and it has an atlas consisting of two charts. We're going to call this the positive chart and the negative chart. So the positive chart is going to be a function from the open unit interval into S1, and it's going to be given by the formula. And you will notice I'm going to be using the letter S. So S is a number from 0 to 1. That it's e to the 2 pi I s. And the negative chart, this is the one that's going to be given by, and as you will see, I'm deliberately using a different letter because I'll be able to tell these two charts apart. That's why we're using a different letter. Psychologically, it's going to be convenient to be able to distinguish between them. So this is going to be negative e to the 2 pi I t. And to remind you how this goes, the positive chart, it takes the interval from 0 to 1, this is f plus, and it's going to wrap it around the circle like this. So this is going to be the point which is missing, and the negative chart takes this open interval and it will wrap it like this. So this is, maybe we indicate the missing point. So that's the missing point. So this chart, its image is everything minus that point, and this chart, its image is everything minus the other point, and you can see that these two open sets completely cover the circle, and these are homeomorphisms and all of that. So we saw this example from the second to previous class when we talked about smooth manifolds. And so the reason for using S and T has to do with this. If I pick a point on the circle, so let's suppose I pick that point right there, then I would say that the S coordinate would be equal to, now you can see with the S coordinate, I'm going, actually I messed this up. I'm supposed to be going counterclockwise. So let me do that again. It goes like this. So the S coordinate would be equal to a quarter. So here S would be equal to a quarter. So the meaning of this, when we say S is equal to a quarter, this means that when you're using the S chart, so you can call this one the S chart, and you can call this the T chart. So when you're using the S chart, the correct value of S that maps to that point would be a quarter, right? A quarter of the way will take you to that point. But if you're using the other chart, if you're using the negative chart, then the correct value of T would be, well, this is half of the way and this is another quarter. So here T would be equal to 3/4. And then we also talk about so we're mapping, so we also do this. So we map the interval from 0 to 1 to 0 to 1. So we map this using f plus to the circle, and then we map this using f minus to the circle. And if you look at the way they intersect, right, the image of this and the image of that, the way they intersect is they will give you the entire circle minus 2 points. So these will be the 2 points that are missing. That's the way the images intersect. Okay, the images. And then when you take this open set and you pull it back to each chart, you would have the missing point, you would have the missing origin, well, not the origin, but you'll have the missing center. And then you have a map mapping this open set to that open set, and that map would be F plus followed by, so this will be F plus composed F minus inverse. So what is this map? So F minus inverse composed F plus. So what does it do to S? So if you give me a point S, so let's say you give me a point S over here, then look what happens with S. The F plus map will wrap it around like that, but then its corresponding point in the T chart would be shifted over by a half. And so what we have here is this is equal to S plus a half if S is between 0 and a half, and it's S minus a half if S is between a half and 1. So basically what we're saying here is this. So basically we have a change of coordinates. What's the change of coordinates? So the change of coordinates is that the T coordinate is equal to S plus a half if S is between 0 and a half, and it's S minus a half if S is between a half and 1. So this is basically change of coordinates. You see what's happening here is if you know S, F plus of S, that gives me a point on the circle, and when you pull it back using the inverse, you're getting the corresponding value of T in the other chart. So you're essentially describing the relationship between S and T. So if you know the value of S, you can recover the value of T, and then you can do it also the other way around. If you know T, you can get S. So this is what we call the change of coordinates. So this function that takes you from one chart to the other chart, that is the function that describes how you change coordinates. Okay, so this is our example. And now I want to give you a smooth function. Let us show that the function re from S1 to R is smooth. So where re of a point on the circle, so a point on the circle is a complex number, that just calculates for you the real part of z. So we're going to show that this function is smooth. So to show that it is smooth, we will calculate re in each coordinate. And when we say in each coordinate, what we mean is in each chart. So we're going to compose it with each chart. So if you do re composed with the positive chart, that's going to give you a map. So let's see what kind of function that is. So you do f plus of s. So that will give you the real part of e to the 2 pi I s. And the real part of that by Euler's identity would be cosine 2 pi s. And if you do re composed with the negative chart at t, that would be the real part of negative e to the 2 pi I t. And by Euler's identity, that would be negative cosine 2 pi t. Now I'm going to show you the sloppy way you write this. So this is what we call, this would be sloppy notation. So sometimes what we would do is we would write re of s is equal to cosine 2 pi s, and we would write re in terms of t to be negative cosine 2 pi t. The reason why this is technically incorrect is because re is defined on the circle. So that does not make sense. Re cannot be evaluated at a real number. But really what we mean here is it's this mapping re, the real part mapping, done in terms of the s coordinate. So when you're doing it in terms of the s coordinate, you're just composing it with that chart. So the coordinate chart for s, that's the f plus. So you're just composing it with f plus, and this is the mapping that you get. Now we can see, so we should observe, so observe that re composed with both charts are smooth functions. Hence, Re is a smooth map from the circle to R. You see, that's the definition of what it means to be a smooth map. That if you compose it with the charts, you get smooth maps. So these are cosines, these are smooth functions. And the other thing I want you to observe, furthermore, so we are getting two functions in each chart. And in each chart, you can also say in each coordinate. In the s coordinate, we get the function cosine 2 pi s. In the t coordinate, that's the other chart, we get the function negative cosine 2 pi t. So these two functions are coherent. So what does it mean to be coherent? Well, what it means is that we have a function, let's call this function f. Maybe I should not call it f plus. So we're going to do it maybe the rigorous way first, and then we'll do it like the more informal way that makes it easier to understand. So the formality here is that you have f plus. Well, you have two charts, right? You have two charts. You have the f plus chart and f minus charts. And these are maps on the open unit interval. Now, so you have f plus. So let me write it like this: f plus from 0, 1 into S1, and you have f minus from 0, 1 into S1. And on each chart, you have a function. So the positive function on the positive chart, it's going to be defined on this interval. This is cosine 2 pi s. So maybe we'll call it a function. I'm already using f. Maybe we'll call it capital F. Capital F plus. This is the function that's cosine 2 pi s. And then and on the other chart, you have a function that's negative cosine 2 pi t. So you have two different functions. And we claim that f plus and capital F minus are coherent. So what do we mean by coherent? It would just mean that, you see, we're mapping 0, 1 into R by using this function, and we're mapping 0, 1 into R by using the other function, but we also have the change of coordinate function f plus composed with f minus inverse. So that would mean that the diagram commutes. So f minus would be equal to the change of coordinate map. Well, I got that backwards. It would be the f plus. Yeah, so this is f plus. That would be equal to f plus. This one would be f minus composed with f minus inverse composed with f plus. That's what we're saying. And is this true? Well, this is the function. You see, this is the function cosine 2 pi s. This, well, this is piecewise. This is either s plus a half or s minus a half. And this is negative cosine 2 pi t. So if you substitute that in here, would you get that? And the answer is yes, you can check. Because if you were to just do, let's say, cosine 2 pi t, so there's like two different cases, but it does not matter which one you use. So I'll do one of them and you can check the other one. This would be negative cosine 2 pi s plus pi. And then you use that identity that when you add pi into cosine, you get the negative of the cosine. So you get cosine 2 pi s. So you're getting the same thing. So the composition is preserved. It's consistent. So because of that, we say that these two functions are coherent with respect to each other. I should say coherent with respect to the atlas. But so this is like the careful way to check it. The quick way to check it is basically this, that you go back to the sloppy notation, and then you would say, what's the change of coordinate? You would say the change of coordinate is that t is equal to either s plus a half or s minus a half, depending on what interval s falls into. And then if you were to replace, so you basically have this function, and then you have this function. So those are the representations of the real part function with respect to each of the two charts. And if you were to replace t by this change of coordinates, you get consistency. They're giving you the same function. So this is often the way we do it, because notation-wise, it's a lot simpler than to write out all of these compositions. But more formally, this is really what you're checking. Now, the fact that these two functions are consistent with each other should not be a surprise, because we had a globally defined function on the circle, and those were just, you can say, the restrictions of that function to the two charts. So it's not a surprise that they will agree with one another because they're coming from a globally defined function. So this is the example that I wanted to show you. But now I want to show you an example of something that is not smooth. So let us show that theta is not smooth. So what is theta? So this is the angle function. Now the problem with the angle function is that the angle poses a lot of difficulties. So we go back to the circle like this, and I pick, let's say, that point over there, and I ask you, what is theta? You might say that theta is equal to 0. But you might also say that theta is equal to 2 pi. So let's say you insist that theta is 0. Okay, so you say theta is 0. Then I ask you, well, what is that? You say, maybe that's theta is pi over 12. Maybe that is theta is equal to pi over 2. Maybe here theta is equal to pi. Maybe here theta is equal to 3 pi over 2. But what happens as you return back? Well, that's 0, and if you stay away from 0, that would be close to 2 pi, but the moment you reach 0, that's back to 0 again. So you have a problem. So there's an issue that happens here. So, I mean, you can also do it on the other side. You can do it really in any way you want, but you can also do it like this. You can also say that if I pick this one over there, you could say that theta is equal to pi, but you could also say that theta is equal to negative pi. And it's a bit ambiguous, and it seems that as you travel around the circle and you return back, there's that abrupt jump by 2 pi that occurs. So it makes sense. There's problems that exist with the angle function. But let's understand the angle function with respect to the s coordinate. Now, more formally, what does that mean? So more formally, i.e., what we mean is the angle function composed with, you see, it's not even clear how to define this. This is a bit unclear, but it will make sense how to define it with respect to each chart. So let's just work it out in each chart, and it would be clear how to define it. So let's do it in the positive chart. So this would be the angle of e to the 2 pi is. And the angle is right there. That's 2 pi is. I'm sorry, that would just be 2 pi s. Because this is the function that takes the interval and it will wrap it around the circle like that. So as you can see, you're staying away from 0 and 2 pi, so there does not seem to be any problems. Like, it makes sense that you define this to be 0, like pi over 2, pi, and then back to 2 pi. And because s is on the open interval from 0 to 1, you never run into this issue of how to define the angle. It seems to be clear how to do it. This winding around, the full wind around does not occur, and so there's no issue in how to define the angle function. This would be the way to do it. But what about the other one? What about theta written in terms of the t-coordinate? So in other words, what we really mean is when we use the other chart, so this would be the angle function of negative e 2 pi I t. So this one, if you think about it, this would be negative pi plus 2 pi t. So let's just explain that, because the other chart, the way it maps this interval is that it takes this interval and it will wind it around like this. So it sort of starts at negative pi, but you can also say it starts at pi. But if you say that it starts at negative pi, then by the time you go around, you should say it's pi. And that makes sense. If you set t is equal to 0, you get negative pi. And if you set t is equal to 1, you get negative pi plus 2 pi, you get pi. And there is no ambiguity in how to define the angle here, because you've not made a full revolution around. So you do not have that abrupt jump that occurs. So it makes sense that in the s coordinate, in other words, in the positive chart, you define the angle function like this. And in the negative chart, you define the angle function like that. Now, what I would like you to observe is these two functions. So clearly, so these two functions are clearly smooth. So does it mean there exists a globally defined smooth function on the entire circle, so that when when you write theta in terms of the s coordinate, you get 2 pi s. And when you write theta in terms of the t coordinate, you get negative pi plus 2 pi t. That's the question. And it's not enough to say that because this function is smooth and that function is smooth, it means that there exists a smooth function that when written in the two coordinates, it will give you this. So we have to check coherence. So the question here is, let us check if the two local representations, that's what we're doing. We're describing a global function locally in each chart. If the two local representations of theta are consistent. So we have to do change of coordinates. So we have theta of s is 2, well, let's write theta of t. Theta of t is negative pi plus pi t. And then we do coordinates. Now we know that t is equal to either s plus a half or s minus a half. So let's say it's s plus a half. Then we would have that this is negative pi plus 2 pi s plus a half. And that will give us negative pi plus 2 pi s plus pi, which is 2 pi s, which is theta of s. So you can see that theta of s is equal to theta of that theta of t is equal to theta of s. However, this is only if we're using the first case. In the second case, will give us a problem. So if you go back to theta of t again, we will have negative pi plus 2 pi t. And now if you use the other possibility that t could be equal to, then that will give us negative pi plus 2 pi s minus pi. So that will give us 2 pi s minus 2 pi, which is not equal to theta of s. So you can see it is not consistent. The two local representations of theta are not consistent. So this means, right? So that means there does not, right? There is no globally defined function called theta, so that in the s coordinate it's given by this, and in the t coordinate it's given by that. And so the angle function if we want to define the angle on the circle, it's not possible to do that on the whole circle in a smooth way. So that's what this example shows. And it, again, illustrates this idea of things being coherent and also not coherent. So now that we have this example, we can move on to something else and talk about differential forms on a smooth manifold. So that's going to be the next topic. Now we are in position to define what a differential form is on a smooth manifold. Let x, comma, let's call this phi lambda, be a smooth manifold. And I should just give you a disclaimer that our definitions will be a little bit different from the definitions you see in most books. They happen to be equivalent, but they do things a little bit differently. I'm trying to define things in the most elementary way possible so that you need to know the least amount of math to understand this. What they do in books is they often define it in a fancier way, but then the price to pay is you have to do extra math. I think for learning purposes, you want to keep it, you try to keep this topic as simple as possible. We have a smooth manifold, and we define, so a differential form, maybe I'll just say a form. A form on X is a collection, let's call this a collection, omega subscript lambda. So this is going back to the idea that anytime you have a smooth manifold, in order to understand the smooth manifold, you just have to understand what's happening on the charts. That's really what we're doing. So if I want to define what is a form on X, I'm just going to define a form on each chart. So it is a collection of forms, where each omega lambda is a form, is a differential form on the lambda chart, on Rn. Okay, so just keep in mind that you have a chart that maps the n-dimensional Euclidean space into X. So instead of defining a form on X, you rather define it on the chart. So this is the lambda chart. This is the chart that corresponds to lambda. So you're defining a form on this one. So this is a Euclidean form, by the way. This is a Euclidean. This is the reason why in the previous lecture we talked about Euclidean forms. We know what differential forms are in Euclidean space. And then the way you define a form on a manifold is you rather define forms on the charts. The charts are Euclidean. So these are just a collection of Euclidean forms, one in every chart. And we want this collection to be coherent. It's exactly what we have with smooth functions. We want them to be coherent. And we want this collection to be coherent. So in other words, this is what it means. It would mean that, so I'll draw it for you over here. So we have Rn mapping something into our manifold. We have Rn mapping something else into our manifold. These might intersect, right? Their images might intersect. Maybe I should actually draw a picture here. So let's say this is our manifold. And Rn, this is Rn, is being mapped by phi lambda onto a piece. And we have another one, Rn, being mapped onto another piece. This is phi mu, and they happen to intersect somehow. And that's the piece on which they intersect. Then this is what we call change of coordinates. This is phi lambda composed phi mu inverse. And we need to understand that this composition is no longer a mapping from Rn to Rn. It rather is a mapping from an open subset of Rn to an open subset of Rn. But this is what that composition is. And now you have a differential form, omega lambda, in the lambda chart, and you have a differential form in this chart. So maybe what I'll do is I'll get rid of, so maybe I'm going to get rid of this one because this one I think is going to be a distraction. I want to get rid of this one. So we have this. We have this change of coordinates function. And on this Euclidean space, we have a differential form, which we're calling omega lambda. And on this one, we have another differential form, which we're calling omega mu. Okay, so we have a form here and we have a form here, and we have a mapping. Now, anytime you have a mapping between Euclidean spaces, that will induce a mapping in the other direction on forms. So like in general, so maybe I should just remind you. So in general, so if U and V are open in Rn, and you have a mapping, let's call it F, from U to V, then you get the induced map on forms. It takes you from forms on V to forms on U. And it's basically given by substitution, that if you have a form on this one, the way you get the other form, F upper star of omega, is you basically substitute in the function into the form. And this is what we talked about last time. This is known as the pullback operation, that a form on the codomain can get pulled back and it gives you a form on the domain. So we're going to use the pullback operation over here. So the idea here is omega mu is defined, well, it's defined on all of Rn, but it's certainly defined on this open subset. And because you have a mapping like this, the pullback operation will transfer over that form to a form on the other open set. And we want them to be coherent with each other. So the condition here would be that if you do phi mu inverse composed phi lambda, the pullback operation on forms, and you apply it to omega mu, you end up getting omega lambda. So if that condition is satisfied, then you say this is a coherent collection. And then you would say that that is a form on X. Okay? So that's the definition of what it means to be a form. So maybe I should just give just a warning here. Forms are not defined on X itself. Rather, forms are defined on charts. You're defining them on the charts. Because these choices that you're making, these are basically coherent choices. These choices that are being made, these are Euclidean choices, whereas X could be some abstract space. So you're making these choices and you want them to be coherent on these transition mappings. And this basically means that when you change coordinates from one chart to the other chart, everything works out to be consistent. So that's the definition. It might be a little bit abstract, but we're going to do some examples that will help clarify how this works. Now, I want to also discuss the differential operator. So I'm going to take this down. I'm going to discuss the differential operator. So we have a differential operator. So maybe I should start with this. C infinity on a smooth manifold, these are smooth functions. Smooth functions on X. And there's two definitions. So definition one, you would say that it's a function from X to R, so that if you do F composed with phi lambda, where this is just a lambda chart, then the map from Rn to R is smooth. So that's one way of defining it. But the other definition, and this definition is actually more useful, because definition 2 is closer to how you work with differential forms. You would say it is a collection. So a smooth function is a collection. So you would rather say this. Let me take this away. So you would say that C infinity x, this is the set. This is the set of functions f lambda, where each f lambda is a map from Rn to R, is smooth. And you would just say that these are coherent. This is a coherent family. So it is a coherent family of functions. The functions are defined on the charts only, but it's a coherent family. So coherent would mean that, well, I'm not going to write out what that means again. So you have two definitions. You can define smooth functions like this, or you can define smooth functions like that. So it's clear that if you have a function of this form, then these compositions will then give you a family of functions on each chart. So basically, this becomes the f lambda, right? So if you just set that equal to f lambda, that gives you a collection of functions on every single one of the charts. And that would be a coherent family for the simple reason because all of these f lambdas are coming from one global function that's defined on the entire smooth manifold. So these are the two definitions. And I think definition 2 is more convenient to use because it's more relevant to how it works with differential forms, because a differential form is just a generalization of that. Okay, and then we define zero forms on X. This is just smooth functions. Smooth functions on X. And I would say maybe using definition 2. So I think this will be more useful for us, because then the notation is more consistent when you get to forms. Okay, and then after that, you can then define omega k of x. You would then say that this is the collection of, this would be coherent choices. It would be a coherent family of omega lambda, where each omega lambda is a k-form on your chart. So instead of writing, I think maybe it would be even better to just replace this and just write it like this. Because we kind of, even though we're saying the same thing, it just says that a smooth function, it's a collection of smooth functions in each chart, but the choices are coherent. So on the overlaps, they agree. So then a k-form would be a collection of k-forms in every chart, which is coherent. So we have an operator, let's call it D, that takes us from k-forms on X to k plus 1 forms on X. So how is it defined? Well, here's the way it gets defined. If you give me a k-form on X, all that is just a coherent family of choices. And how do I create a k plus 1 form on X? So all of these are forms on the charts, on every chart. So how do I get 1 over? Well, you just apply the differential operator to each of these, because these are now Euclidean forms, so we know how to do that. So this would just be d omega lambda. So you do have to check, one does have to check that that this defines a coherent family of k plus 1 forms. So you do have to check that, but assuming that this is true, if you're willing to accept this fact, then you have just, you see, these are k forms defined on every chart. When you apply the exterior derivative on these Euclidean forms, you increase their degree. So these become k plus 1 forms defined on each chart. So assuming that this new collection of forms is coherent again, right, assuming that is the case, then you have defined a family a family of k plus 1 forms in each chart in a coherent way. So by definition, that gives you a k plus 1 form on X. So that's what we have here. So this is the definition. And it would be nice to give an example that illustrates this. So I'm going to take this down, and we're going to go through an example, and we'll see how it works. Let's use our example with the circle again. We had a circle, and we had an atlas consisting of what we call F plus and F minus. And F plus was the chart that was given by e to the 2 pi is, and F minus of t was given by minus e to the 2 pi it. These were maps, of course, from 0, 1 to the circle, 0, 1 to the circle. And we previously saw that the family, and let's call this family theta plus, theta minus, where theta plus of s is 2 pi s, and theta minus of t was negative pi plus 2 pi t, does not define a coherent family. For the simple reason because the change of coordinates from the S chart to the T chart, that these two functions are not consistent with each other. So this was the example that we did very carefully. And therefore, so thus, there does not exist a smooth function, or in fact any function, not just smooth, let's call it theta, with theta in the positive chart being equal to theta plus s, and theta in the negative chart being the other one in the family. Because if there was such a globally defined function, the restrictions, maybe I should not say restrictions, it's not the best terminology, but the restrictions to each chart would then be consistent with each other because they're coming from a globally defined function. Now I want to show you something interesting, that let's apply the differential operator to this one and to that one. So something interesting will happen. However, the family d theta plus and d theta minus will be a coherent family of one forms. So let's check that. First of all, what do we mean by d theta plus? So here's what you need to understand. The notation might be a little bit confusing because theta by itself, well, theta technically does not even exist, okay? So there is, but when we write theta, what we want to say is there's a globally defined function on the circle. However, when we write theta plus and theta minus, these are no longer defined on the circle. You see that? They're no longer defined on the circle. These are actually functions on the charts. So you bring it back to the charts. You bring it back to Euclidean space. So these are actually functions on the charts. You call those like local representations, local coordinate representations of this theta, assuming that such a theta even existed, but it does not exist. And when you calculate these exterior derivatives, you're going to calculate the exterior derivatives in the Euclidean sense, right? This is a function. This is a function. This is a smooth function. And anytime you have a smooth function, you can talk about the exterior derivative of the smooth function. So this is a function of a single variable. So its exterior derivative would be a differential form with just one single generator. So, and in fact, this form will be, we're going to write this as you differentiate this. So this would be 2 pi D. That's what this is. So this is a one form defined on this chart. And d theta minus, this is the other one. And it's convenient to use a different symbolic. The symbolic that you use does not really matter, but psychologically it's convenient to tell them apart by using a different letter for each chart, so you know from which chart it's coming from. So by using the letter T, then we're knowing this is the exterior derivative on the negative chart. So this one will be, you differentiate this one, and that will give us 2 pi dt. Okay, so we have a form, we have this form, and we have that form. And we claim that these two forms are coherent. So we claim that this is a coherent family. So how do you check it's a coherent family? Well, this is the way you do it. You have a map from 0, 1 into the circle. You call this F plus. You have a map 0, 1. We call this F minus. And you have a change of coordinates map, which is theta plus composed theta minus inverse. That's the change of coordinates map. And the change of coordinates map, what it does is that it takes S and it maps it to, well, there's two possibilities that we've talked about. It's S minus a half or S plus a half, depending on whether S is between a half or a half and 1. So this is the change of coordinates map from this one to this one. And now we have theta plus. So we have 2 pi s. So here we're going to be using the symbolic s as the variable for our function. And here we use the symbolic t for the variable for our function. The differential form that we're getting, this is a differential form that is defined. So when we say the differential form is defined, we just mean the coefficient functions are defined on this interval. So we have a form over here, 2 pi s, 2 pi ds. And we have a form over here, 2 pi dt. And we need to check coherence. So the question here is, we need to check to show that if you take this form, 2 pi dt, and you apply to it the pullback operation, right? The change of coordinates, this is the pullback operation. You get, it transforms this one to the other one. So is this true? And the simple way, so the way you transform forms, right, the pullback operation is basically substitution. So the pullback of a form is substitution. So look at what you're doing. The change of coordinates function, it takes s and it sends it to t. So t is a function of s. That's basically what you're doing. So this change of coordinates map, maybe for simplicity, I'm just going to call it g, because I do not want to keep on writing that composition. So you have g, it goes from s and it goes to t, right? It takes a point in s, it takes you an s coordinate and it gives you a t coordinate. So the idea here is that the t that you have, right, you want to determine how you transform this one. The t that you have gets replaced by whatever that function is. So you're going to have, therefore, 2 pi dt, but you're going to apply the exterior derivative to this function, to this mapping, right? This mapping is g, which is basically that function. But so this would therefore be 2 pi, but the exterior derivative, what's this mapping g? It's s minus a half, s plus 1/2. When you differentiate this, this is just the derivative of just s, right? That would just be ds. And these are constant, so these just will not be there. So this would just be ds in the end. So we get to see that when you apply the pullback to this form, you get the other form. So you have coherence. So that's how we're getting the coherence. So what does this mean? So let me take this away. So this is a coherent family. So we have a coherent family, and we just denote this coherent family. So here's something interesting. We denote this coherent. Well, maybe before I do that, So thus, we would say that d theta plus d theta minus, that's an element of one forms on the circle. That's what you would say. Because a one form on the circle, it is a collection of forms in each chart of the atlas that are coherent. So this is a choices, that's choices of forms in each of the charts, a coherent choice. So all of that will now be a one form on the circle. So you have to understand, it's a bit confusing because these functions, theta plus and theta minus, are technically not defined on the circle. They're defined on the charts, which get mapped into the circle. But you kind of bring everything back to the charts. So we abuse notation and simply write d theta is an element. It's a one form on the circle. Now, the reason why we're abusing notation is because if you want to be very precise about this, strictly speaking, theta from the circle, theta does not even exist. Because when you write theta in the two coordinates, theta plus and theta minus, right, going back over here, this family is not coherent. This is not a coherent family. So a globally defined function does not exist. However, something really interesting happens when you calculate the differential, the exterior differential of this one and of this one, then you now get a family of one forms that are globally defined. Well, maybe I should not say globally defined, but it's a coherent. So when we write d theta, what we really mean to say is, we really mean to say that. Because what we're trying to say is, we're trying to say there's an angle function in each of the two charts. The angle function cannot be globally defined in a smooth way. However, if you were to take the two local representations of the angle function in the two charts, and then you find the differential of its local representations, then you end up getting a globally defined, well, a coherent family of differentials. So then you say this family is now a one form on the circle. And you just abuse notation by just writing d theta, but strictly speaking, you really mean this. So this example just illustrates by what we mean by a one form. And we'll do another example involving a torus, which will be sort of inspired by this. The last example that we're going to look at is going to involve a torus. So here, we're going to think of the torus as a product of two circles. This is going to be the convenient way of working with the torus in this example. And this is a smooth manifold. For the simple reason, because a product of two smooth manifolds is, again, a smooth manifold. You had that question as a homework problem, but just to show you how you would do it is, you basically use the chart for the circle, and you just repeat the chart twice. So I meant to say the atlas, not the chart. But the way you would do it is, you would say that S1 has the atlas, the smooth atlas, F plus of S in terms of S, and F minus in terms of T. I'm not going to write down again what these functions are, because we've seen that already a few times, but S1 has an atlas. And then you can just repeat these to get an atlas for the product. So then S1 cross S1 has an atlas given by the following collection. So you would just take the different combinations of these. So you can have the function f plus times f plus. You can have the function f plus times f minus times f plus, and then f minus times f minus. If you're not sure what I mean by that, let me illustrate this for you by let's say using the first one. So f plus times f plus. So this is a function. And now you're going to have, since the torus is a two-dimensional manifold, you're going to have two coordinates. It's going to be something in R2. So let's say we call the coordinates S1, S2, because we're going to have two of them. And then this is going to be given by, well, it's the first function followed by the second one. So that's going to be f plus, that was the function e to the 2 pi I s1, comma e to the 2 pi I s2. And this is going to be a point on the torus. And then this one over here, f plus times f minus, that would be the function. So we need to come up with a pair of variables to describe the function so that we can psychologically talk about which of the four coordinate systems we're going to be using. So let's say this is the coordinate system that's going to be denoted by s1 comma t2, and that's going to be the f plus function, so that's e to the 2 pi I s1, and the f negative function, which was the function negative e to the 2 pi I t2. Also, I should say that the domain for this function, this is a function from the open square into the torus, because these two functions individually are on the open interval, and this function is also on the open interval, mapping it into the torus. And the same thing would happen with all of these. So the open interval is, of course, homeomorphic to R2, but it's just more convenient to keep it in the notation of the open interval. So you're mapping basically, I mean, the charts are all homeomorphic to R2. So you're mapping copies of R2 homeomorphically onto the torus. And you have to check that this is an atlas, that it satisfies all of the conditions that an atlas is supposed to, and that it is smooth. But you had that question on the homework, that if you, so in general, if you have a smooth manifold and you have another smooth manifold, then by considering all combinations of the charts, then you will get a smooth atlas for the product space. That's not that difficult to check, but assuming that you're willing to accept this, then you have an atlas for the torus consisting of 4 charts. And the variables here, so this one over here, we're going to call this one so the first one, we're going to call this the S1, S2 coordinates. The second one, we're going to call this S1, T2 coordinates. This one is going to be T1, S2 coordinates, and then we would have T1, T2 coordinates. Okay, so basically what this means is that you have your torus, okay, and if you pick a point on the torus, I can ask you what are the S1, S2 coordinates of that point. So that would just mean what is the correct choice of S1 and S2 that you need to use under this mapping to get that point. But I can also ask you different coordinates. I can ask you, let's say, what is S1 equal to and what is T2 equal to, right? I can also ask for S1 and S2 coordinates. So the same point can possibly lie in many different coordinate systems, right? In many different charts. So these are just, this is what we call local coordinates, that they describe a local piece of the torus. And taken together, they globally cover the entire torus, and every point is located in at least one of those charts. Some points will be in all of the charts, but like in general, a point in random will be in all 4 of them, but at least it's always in at least in one of those 4 charts. And in a very similar way, so similar to the circle, there are 2 angles, theta and phi, on the torus, right? Which is not surprising because you have 2 circles, right? You have an angle for each of the 2 circles. And the picture here is, of course, that one of the angles tells you how much you go around the inner ring, and the other angle tells you how much you go around the outer ring. But the issue is that these 2 functions cannot be defined smoothly on the torus for the same reason as on the circle, because as you go around, when you make one complete revolution, then the angle jumps from 0 to 2 pi. And that's why it's not possible to define these angles coherently and in a smooth way throughout the entire torus. So, and if you were to write out these angles in terms of the coordinates, then this is what you would get. So it is not possible to find a smooth function, a globally defined smooth function on the entire torus, so a real valued smooth function on the torus, so that when you write out this function in each of the 4 coordinate systems, so when you write it out in terms of, let's say, S1 and S2, so let's say theta is referring to the first circle, and phi is the angle referring to the second circle. So then theta would be determined, it's basically the theta from before where you only pay attention to this one. So that would be 2 pi s1 theta of s1 t2. When you write it out in terms of the chart, this would be 2 pi s1 theta in terms of the chart t1 s2 would be negative pi plus 2 pi t1, and theta in terms of t1 and t2 chart, negative pi plus 2 pi t1. The reason for this is because, as we saw, this does not define a coherent family, because the way you change coordinates from t1 to s1 is t1 is either s1 plus a half or s1 minus a half, and depending on which one you pick, it's not the change of coordinates will not be consistent with that one. So you can define theta smoothly on each of one of the four charts, but not globally as a smooth function on the entire circle. Right? However, d theta is a global one form on the torus. So even though the angle is not, d theta is a global one. But what do we mean by d theta? So again, this is really abuse. Here we're really abusing notation, because technically theta does not even exist. But what we really mean to say is theta, if it did exist, its local representations in each of the charts would be given by these four. So then d theta, the way you calculate the exterior, the way you would then calculate the exterior derivative of a smooth function is you would write the smooth function with respect to the charts, and then you will just calculate the exterior derivative in each chart. So then d theta, so here d theta is equal to, and this is really by definition, this over here, this is just a shorthand way of saying what we're about to say. You just calculate the exterior derivative of all of these. These are functions on the square, on the open square, this on the Euclidean open square, and you can therefore calculate their exterior derivative of all of these functions. So for this one, so on this chart, this function, its exterior derivative would be 2 pi ds1. This one would be 2 pi dsn. S1. This one would be 2 pi dt1, and this would be 2 pi dt1. And this, so this is an element of, this is a one form on the open square, because that's the chart. This one is a one form on this open square, and so on. They just have different corresponding coordinates. So here the coordinate system is denoted by S1, S2. Here this is the chart that's denoted by coordinates S1, T2. This is the chart whose coordinates are denoted as T1, S2. And this is the chart whose coordinates are denoted as T1, T2. But all of these are one forms defined on the open rectangle. Okay? And this is coherent for the reasons that we've explained before. This is going to be coherent. And in a similar way, phi, but maybe I should say this, in a similar way, there is no globally defined angle that goes around the other circle on the torus that is globally defined and is smooth. However, d phi is a globally defined one form on the torus. So that's the way we would write it. So what do we mean by d phi? So by definition, a one form on the torus is, by definition, it is a one form on each of the charts, on each of the Euclidean charts. So this would just mean the same thing as we have before, except you just do it with the other one. So this would be, so this one, you can guess what this would be. This would be 2 pi ds2, 2 pi dt2. You see, I'm basically just looking at the coordinates here. On the second one, this would be 2 pi ds2, and then 2 pi dt2, like that. Okay, So that will give you a coherent collection of one forms. Okay, and now, so just like we can multiply, and by multiply we also mean wedge. Just like we can wedge forms in Euclidean space, we can likewise wedge forms on a smooth manifold. So what we have is, since d theta and d phi are globally defined one forms on our smooth manifold, it means that you can wedge them. And then when you wedge them, you will now get a two form, a globally defined two form on your torus, on your manifold. But what is the wedge? How do you find the wedge? Well, it means exactly what you think it means. So if you really get this, if you really are understanding this, then it means exactly what you think it means. So where means, then this is really by definition. This is the reasonable way you would define the product of two forms on a manifold. That would just be equal to, well, this is going back to the main idea. The main idea is, anytime you work on a manifold, you bring everything back to the charts and you do all of your calculations in the charts. So what does it mean to wedge these two forms? I do not know, because we have an abstract space. But each of these two forms can be brought back in terms of Euclidean charts. And then all I'm going to do is, I'm going to take these two forms and I'm going to wedge them, right? This form, this is a one form defined on that Euclidean space. This is another form defined in the same Euclidean space. Both of them are coming from the same coordinate system. And I just multiply these as you multiply forms. It's just a formal product, this one multiplied by this. So that would be 4 pi squared ds1 wedge ds2. So that would just be 4 pi squared ds1 wedge ds2. And then you can do it with the other one. The other one will be 4 pi squared ds1 wedge dt2, and then 4 pi squared dt1 wedge ds2, and then 4 pi squared dt1 wedge dt2. So this entire family, this is a coherent family, right? This is a coherent family of two forms on each Euclidean chart. And since it's a coherent family of two forms, that means it's an element by definition of that space, right? The set of two forms on the torus, right? The set of two forms on the torus is, by definition, it is a family of two forms on each chart which are coherent. So that's what that would mean if you write it out explicitly. Now, we usually just write something like this, for instance, right? This is more convenient to write than all of that, but hidden behind this simplistic notation is the understanding that theta is not globally defined, but d phi is, okay? And what is d phi? This is what we've written out over here, and this is d theta, and that is d phi. And then to wedge them, you just wedge them in each of the coordinates, and that will define for you a coherent family of two forms. And so by definition, that's an element of the two forms on the torus. So now maybe this is not clear, of course. Maybe the question here is why, right? Why? Why are we doing this? This is unmotivating. So the reason is that, as we will see, and you just have to be patient, right? Just be patient. So as we will see, differential forms are invariant under coordinates. And the reason why we need this is that this is what will make calculus possible. So for instance, let's go back to the torus again. So here's our torus. Let's say we have a curve on the torus. And I ask you, how do you integrate over the torus? That's our space. I'm sorry, not over the torus. How would you integrate over that curve? So you have your curve, some function, f. Like, what would that be? Well, the issue would be is you can map this curve back into a chart, right? You can find the chart. Well, in this case, our charts were really defined on the open rectangle. So you find the chart, and then this is the corresponding curve in that chart, right? Assuming it fits in the entire chart. And then what you would do is you would map the calculation back into the chart, and then you would do the integral as a regular Euclidean integral in that square, right? You would just integrate a function over that curve. But the problem occurs is, what if you have a different chart? And then this is the corresponding curve in the other chart. And what would happen if I was to integrate this in the other chart? Well, what will happen is that in general, you will get different answers. And you're supposed to get different answers, because the moment you go to a different chart, the functions that you're using, they change. Everything changes. And you're going to get different answers. And so this is actually problematic. But what is not problematic is that if you integrate over a form, if you integrate over a differential form, then the differential form will change in the correct way so that it would not matter how you do the calculation. At the moment, it might not be clear how exactly that happens, but we're going to reach that, and then you will appreciate the reason for why we're talking about differential forms. And I believe this is exactly the motivation that led to the development of differential forms. That historically, you did not have a mathematician who just made this up. Historically, what happened, that somebody wanted to invent a new type of object which remains invariant under coordinates. And it naturally led to differential forms. But of course, when you learn about differential forms, you're just kind of told automatically what they are without the motivation. So we're kind of learning what they are first, and then you will see why they have the desired property of being invariant under coordinates. And once we do that, we'll be able to do calculus on a manifold. And that will allow us to solve problems in topology through the use of calculus. And we're leading up to that gradually and very slowly.